Moving on to the next talk in our workshop, we have Amar Phanisayee from Microsoft Research presenting on Project Fiddle, fast and efficient infrastructure for distributed deep learning. Dr. Amar Phanisayee is Senior Principal Researcher at Microsoft Research in Redmond. The goal of his research is to enable the creation of high-performance and efficient networked systems for large-scale data-intensive computing. His research efforts center around radically rethinking the design of data center-based systems, from infrastructure for compute, storage, and networking to distributed systems and protocols that are scalable, robust to failures, and use resources efficiently. His recent focus has been on leading Project Fiddle at MSR, Project Fiddle Microsoft Research. Amar received his Ph.D. in computer science from Carnegie Mellon University in 2012. His research work has been recognized by awards such as the ACM SOSP Best Paper Award and Carnegie Mellon's Ellen Newell Award for Research Excellence. Dr. Amar, I encourage you to share your screen and start your talk.
Sounds good. Thanks.
Thank you.
I don't think I'm rarely called doctor, but it reminds me of the PhD comic joke where, I'm a doctor, but, the useless kind who doesn't save lives. So, Thanks. And I see that there are a lot of people on a Saturday evening. This is dedication. Kudos to you guys. So let me share my window. Please let me know when that's visible.
Believe me, we are all drinking.
Good.
Yeah, your screen is visible. Thank you.
Good, great. Okay, so I lead Project Fiddle at MSR, where over the years, my colleagues and I have worked on building super fast and efficient research systems for distributed deep learning. Specifically, over the years, our focus has been on DNA training, but we've also taken a very hard look at some important problems in the inference space. If my clicker works, there we go. So the problem that we're trying to tackle in Project Fiddle is to systematically speed up distributed DNN tasks while eking out the most from the resources that are used. And so, this is where in the problem statement itself, we wanted to make sure that efficiency was a first-class citizen in the problem that we were trying to address. We did not want to, I jokingly say, we did not want to repeat the sins of our predecessors in big data processing, who used thousands of accelerators to do things like sorting and word count and such, only to realize later on that you could do this using far fewer resources. And the goal in Project Fiddle, the goal that we set for ourselves is 100x more efficient training. So, going 100x faster, say using the same number of resources. Intuitively, what that means is if your model takes a day to train, we should be able to train finish the training in your 15-minute coffee break. Right? And this admittedly is a very, very challenging research goal. And as systems folks, the approach we take is to cut across the system stack, identify all the relevant bottlenecks that might be present for a particular workload, and then optimize all those relevant parts of the stack. So I'm a visual thinker. So I'm going to show you an image as to the scope of the problem that we've tackled over the years. So we look at training, the broader picture of training, all the way from a single accelerator. So you can think of this axis here, the x-axis, as sort of the scale axis. From a single accelerator to multiple accelerators still on a single machine to massive clusters at Microsoft that use thousands of accelerators, thousands to tens of thousands of accelerators. And we cut across the stack, system stack. So that's sort of this vertical axis. By looking at the memory manager, the memory subsystem, how to structure computation, how to optimize communication between accelerators on the same machine and across machines. the storage layer, so both the ingest as well as the output pipeline. And you can think of all these up until this point on the vertical axis as innovations that help speed up individual jobs. But then we also have zoomed out and looked at massive multi-tenant clusters at Microsoft, analyzed problems that exist at that scale. And based on those findings, apart from releasing traces and failure analysis for such clusters for the broader research community, we've also been able to use that to motivate the design of completely new cluster schedulers that tackle sort of very specific aspects of the problems that we had identified at Microsoft in these large clusters. And finally, cutting across all these things, we've looked at algorithms and tools that help in this whole process. Let me walk you through the stack a little more carefully. But for each of these things, if you're interested, all this work is out in the open. And we've published all these in papers that you can find on the Project Fiddle website. And they've been, I don't know if you follow these communities, but they've been published in sort of the top conferences for systems, operating systems, distributed systems, networking, databases, and ML conferences like NeurIPS and ICML and such. So let me walk up this stack a little more carefully. And for the remainder of the talk, I'll focus on one specific sub-project in Project Fiddle, and we'll do a deep dive in there. Right? So revisiting the stack, we initially started just by looking at a single accelerator and asking the question, how much more could we do with a single accelerator before we asked for the second accelerator? Right? This ties into this notion of efficiency that we had in our in the initial problem statement that I showed you. And so specifically, we were looking at the memory subsystem there. One of the first things that we found was many of these models for training would hit memory capacity limits before they hit peak flops, peak advertised flops for the device. This is kind of a little funny and shameful because here we are paying through the nose for many of these accelerators, especially if you're cloud providers like Microsoft, Google, or Amazon. You have to multiply this by the massive scale that these cloud providers run it. And it's a shame that we aren't even able to use a single accelerator well enough. Right? So in this particular piece of work, we were looking at the memory subsystem specifically and how to work around the memory capacity problems that many of these models were facing. And the idea was primarily in training, you have these data structures that are generated in the forward pass and later on used in the backward pass. And so we were, in GIST, we were looking at how to encode these data structures so that they occupy a lot lesser memory so that you can load a larger mini batch size or a larger model on the same GPU, right? On the same accelerator, an individual accelerator. On the other end of the spectrum, you naturally have to use a lot of accelerators to make training go faster because parallel training results in faster training time. But also because models are growing larger in size. There are two trends. One trend is models are growing smaller in size for inference on embedded devices. And the other trend, especially for language models, one of the trends we've noticed is these language models are growing to be massive in size. Right? We've already outgrown these models fitting a single accelerator. But even if a model fits in a single accelerator in PipeDream and its derivatives since, PipeDream 2BW, PipeDream Flush, and so on and so forth, we were asking the question, what is the right way to systematically parallelize a DNN workload? And in asking that question, we were able to come up with entirely new ways of parallelizing these workloads. So PipeDream was one of the first to propose a systematic combination of interlayer model parallelism a technique we call pipelining, which is tricky in a pipeline because you have a bidirectional pipeline of forward and backward work, and data parallelism. And there were appropriate algorithms and tooling that would automatically tell you what is the best configuration you should be running at, and compilers that would generate code that would run things in the runtime. More recently, Pipedream has also incorporated intra-layer parallelism into the mix, Megatron-style intra-layer parallelism. And so really, this is a systematic exploration of parallelization across various dimensions. So that's Pipedream. And while we were looking at this for small scale and even massive scale parallelism, we also were asking a question about democratization of these models. So we've already reached the point where these models are so large that many groups cannot even fathom training these models because you need thousands of accelerators to train these models. And so we were asking, what would it take to enable people to be able to develop and debug such models, potentially not train them end to end, but be able to fine tune these models on modest deployments. So think if you had a single DGX1 box or a DGX2 box with 8 to 16 GPUs, what stands in the way for you to be able to train these large models? Turns out today, the way frameworks are written, it's not even possible to train these large models on modest deployments. And so in Harmony, we were asking, how should frameworks, we need a rethinking of how frameworks ought to be scheduling work, and how can we do that? Right? Moving up the stack, with respect to communication, we've looked at how to auto-generate throughput optimal collectives. So this is a program generating a program. It's protocol program synthesis that, given a deployment, we can auto-generate collectives such that we achieve optimal throughput for the given deployment. Current collectives, such as Nickel, use either ring-based collectives or binary tree-based collectives that far underutilize the available hardware, especially in scenarios where a multi-tenant cluster is completely unaware of the topology within a machine as to how GPUs might be connected within a machine. And so it might provide allocations to a job where a ring, for example, might not be possible over peer-to-peer connections across GPUs, and you have to fall back on PCIe for communication. Right? With auto-generated collectives, such problems go away. And finally, for individual jobs, we've looked at problems at the storage layer, both the ingest pipeline as well as the output pipeline, storing checkpoints. And I'll spend the rest of the talk talking about one of these, just looking at the ingest pipeline so that we can sort of dig deep. And I'll show you how, give you a concrete example of what we can do at sort of the algorithmic and systems level to alleviate the problem of underutilizing hardware available today. Right? And I think, so I already alluded to schedulers that we've built. We've looked at problems in multi-tenant clusters, cluster schedulers, and using that, we've been able to build schedulers that target things like fairness, heterogeneity, which we observe in sort of multi-generational clusters here at Microsoft. Those are just a couple of examples of the different schedulers we've built over time. So for the rest of this talk, let me dive deep into CoorDL, which is a new input data processing library that we've built for DNN training that was recently presented at VLDB. So I guess this is a talk later in the day in a workshop where a lot of people might have talked about DNN training. So this might be preaching to the choir here, but let me just go over this so that we set the stage for CoorDL appropriately, right? So DNA training, the input pipeline, if you look at it, DNA training is scheduled in terms of epochs, and in each epoch you process the entire data set. By the way, I can't see. I can only see my screen. I can't see what's happening on chat or if anyone has raised hands, etc. But just feel free to unmute yourself if you have questions in between and ask me if you have any.
Sure, we'll take questions at the end of the talk, and
Okay.
I think we hopefully have time for questions and answers.
Sounds good. Yeah, sounds good.
Yeah.
Sounds good. Thanks. So in each epoch, the entire data set is processed, but within the epoch, the data set is randomized, and we're going to perform random data augmentations to this data. So the training, end-to-end training can be divided into, say, these n epochs, and within every epoch, we have what we call mini batches of data that are being processed in every iteration. And in every iteration, effectively, what's happening in the data pipeline is there are some threads that are prefetching data. This could be, from the storage subsystem that is present locally, such as hard disks or SSDs, or it could be from a remote file system. Then fed to threads that pre-process the data. So, this pre-processing step might involve something like decoding of images, transforming them, rotations, crops, zooming into particular images, etc. And then collating a whole bunch of these different images. And I'm taking the example of images here, but this applies equally to other kinds of data. For example, similar augmentations, etc., are performed on audio data, right? And then collating all these items together and feeding them to an accelerator, a GPU, or a set of GPUs in this case, in this example. And I've shown here pre-processing happening on the CPU, but it could very well happen on the GPU too. So for example, data loading libraries such as DALI from NVIDIA allow you to select where you want to perform this pre-processing, whether you want to perform it on the CPU or the GPU. In fact, in a lot of our experiments, we perform them on the GPU too. Right? But anyway, for this example, I'm just showing it as happening on the CPU. So at the very high level, an iteration can be thought of as actual compute happening on the GPU, and then there's some stuff that's happening before compute happens for data loading. So fetching the data item from storage, and then sort of pre-processing it, right? And the key thing to remember here is that in theory, this is all happening in parallel. It's a pipeline. It's truly a data processing pipeline in theory, right? So when you're doing compute for some batch K, you're actually doing pre-processing for some batch K plus 1, and then you're prefetching data for batch K plus 2. Right? So ideally, this is what you would see, right? You would see compute happening for some batch, and when that compute is happening for the next batch, really we're loading and pre-processing data. Ideal scenario. In this scenario, there are no data stalls, right? But it turns out that in most scenarios today, you actually have data stalls occurring because the stuff that's being prefetched, that's actually in the critical path. It's taking more time than compute itself. And what that means is your GPU now in this particular black portion here is sitting idle, not doing work. And so your iteration time blows up because of data stalls. Right? So iteration time basically now becomes compute time plus data stall time because you're not able to hide this data stall. Let's take a toy example. It's based on some real numbers, but let's just call it the toy example for now. So here, it's the same data processing pipeline I showed you before. We have these 8 V100 GPUs, and we're doing ResNet 18 training, right? And so we have pre-processing occurring on the CPU and then prefetch occurring, right? And our data set is large enough that it all can't fit on a single server's memory. In this particular case, we had 500 gigs on the memory of memory on the server. And open images data set doesn't even sort of fit in memory. About, let's say 35% of it is cached in this case. So for 8 of these GPUs, sorry, that number just went by, but let me highlight it. The ingest rate requirement, right? So they're performing compute and then asking for data. And the ingest rate requirement might be as high as 2.2 gigabytes per second, right? But if we're using, say, hard disk to fetch data, then including cache hits, really, we'll only get 23 megabytes per second, right? So now we incur fetch stalls, and you'll see that this is 2 orders of magnitude lower than the ingest rate requirement for this particular workload. We can use, so this would mean that for a lot of the workloads we see fetch stalls. But if you use a faster storage device, such as an SSD, say for example, our data stall shifts from a fetch stall to prep stalls, because our prep pipeline is not able to keep up with sort of the ingest rate requirements too. So here we have about, let's just squint at that and say 800 megabytes per second is the output of the prep pipeline, whereas we're requesting 2.2 gigabytes per second. So this results in prep stalls. So I'm just giving you very concrete examples of data stalls that I've divided up into fetch stalls and prep stalls. Right? Really, in the VLDB paper that I alluded to, we have analyzed a whole host of configurations. So, while this problem has been looked at, it hasn't been looked at as deeply. The problem of, what role does the input data pipeline play in DNN training? And our paper investigates sort of various dimensions of this, from scale to different workloads, to different kinds of data stores, be they local or remote data stores, different GPU generations, how many CPUs you have, data set size, whether it fits in memory or does not fit in memory, different frameworks, and so on. And surprisingly, across the board, this problem of data stalls exists. Right? Let me sort of take you through some key findings by zooming into some of them. I encourage you to look at the VLDP paper if you're interested in the whole sort of sweep of that space I showed you, but I'll show you some very specific takeaways. Right? So, as the first thing here, I'm just showing only a handful of DNNs. But if we consider only a single accelerator, single V100 GPU, and assume that the entire data set could be cached in memory, here I'm plotting sort of throughput with respect to how many cores am I allocating this job. It turns out that for many jobs, you see this sort of petering out, meaning at some point, the number of CPUs you have are enough to feed this single GPU. But for other jobs, even with all the CPUs on that machine, you're unable to saturate sort of the ingest rate requirements. Right? Remember, I'm showing you just a single GPU here. Really, on modern servers, even sort of the best of the DGX2s, you might have far fewer CPUs per GPU. So, DGX1, for example, has, I think the DGX2 that we have in our lab, for example, has 3 CPUs per GPU. Right? So we'll be operating it sort of in this regime. To drive home that point further, here's the same experiment where we have 8 GPUs doing the training for all these different sort of image classification, object detection, audio processing models. And on the y-axis, I'm showing you prep stalls. Remember, again, the data fits entirely in memory in this experiment. And so there's no fetch stall. Really, prep is the bottleneck. And you'll see that what I'm showing you is percentage of epoch time. So really, prep is a bottleneck for many of these, especially when you're here in this multi-GPU regime. So we're using all the CPUs available on that server, but the ingest rate requirement too has gone up because we're using all 8 GPUs on the machine. Right? Furthermore, right, if the data set is much larger than available memory, which is normally the case, then if you have a scenario, say, for example, where 35% of the data is cached, the focus basically shifts from prep stalls to fetch stalls, because now you have to go to a slower storage device like an SSD or a hard disk or even over the network to fetch this data. And so, fetch times really start dominating epoch time. And the main reason this is happening is because other than the fact that you have to go to disk to fetch stuff, turns out that the OS page cache is horribly inefficient. In the name of generality, it's ignoring workload characteristics. And I'll show you how we can do a lot better if we ask the OS to just get out of the way. Right? And finally, there's a bunch of redundancy in data processing and fetching that is present in this pipeline. So let's dig into this a little more. But before we do that, generalizing the whole thing, data stalls exists when, if the ingest rate requirement is G, if G is greater than either the prep rate or the fetch rate, we're going to have data stalls. Okay? And so one takeaway here is that we can potentially build balanced systems where we're balancing these different rates. I'm not going to talk about that in this talk. We have a piece of work that looks at how to change schedulers to basically look across jobs in a multi-tenant cluster and take away from a job that doesn't need as many CPUs and memory and give to jobs that potentially need them, right? Thereby balancing each of them. But I'm not going to talk about that in this talk. Instead, I'm going to focus on individual jobs. And I'm going to tell you a little more about CoorDL, where the primary question we were asking was, how can we eliminate these DNN data stalls that I showed you on hardware that's present today, right? No need to change hardware. On hardware that's present today, how can we do better? And so primarily, there are three main insights in CoorDL. The first is the OS page cache is horribly inefficient and results in thrashing. So let me, as I told you, I'm a visual person. So let me take you through first being grounded in numbers and then explain why we're seeing what we're seeing. So because the OH page cache errs on the side of generality, it doesn't know about our specific workload. Right? It isn't aware of DNN data access patterns. So the effect of this is, if you take this example where we have 8 V100 GPUs, 500 gigs of RAM, we're training with OpenImage's data set, we're able to cache 65% of the data. And so you would expect 35% misses, right? So those 35% accesses should go to disk. But it turns out if you use state-of-the-art, even state-of-the-art data loading libraries, you see a significantly higher cache miss rate, right? And the primary culprit is the OS page cache. But what this results in is, because you're having these cache misses, you're going to slower storage a lot more frequently, and hence face fetch stalls. Right? So specifically, why is this happening? What is the OS doing to mess all this up? Let's imagine this is our data set, A, B, C, D, and we're going to have these two, look at these two epochs, epoch number n and epoch number n+1, right? And epoch n, we're going to randomize this data set, and we're going to access B, C, A, and D. And in epoch n+1, we're going to access the same thing again, except in a different order, C, B, D, and A. Okay. And let's assume, for the time being, our page cache can have 2 of those four entries, right? So this is our epoch n, and this is our epoch n+1. So, in the prior epoch, let's say D and B were present in the cache. Now, when B is requested, hey, that's in the cache, great. Next, when C is requested, it's not in the cache, we're going to kick D out. And so now we have C and B, right? And so on and so forth. When A is requested, A is not in the cache. We bring A in, we kick B out, and so on. So this is epoch n. And in the next epoch, when C was requested, remember, we had brought in C at some point into the cache, but we had to kick it out, right? And so when C is requested again, in the next epoch, there's a miss, and so on and so forth. So here I'm showing you sort of an adversarial situation in which the next epoch, basically every fetch is a miss. Right? And so basically, our OS page cache, because it was unaware of the fact that we were actually going to touch every data item, despite all these items being in randomized order, kicking them out of the cache has basically caused this problem. Right? Instead, CoorDL uses a crazy simple idea. It's called the min.io cache, which is an application managed cache. It's managed by the CoorDL library, but it does away completely with this idea of cache evictions. It caches stuff, and once stuff is present in the min.io cache, it doesn't kick anything out because we're going to definitely need those items in the next epoch. Right? So in the same situation that I showed you before, the timeline below is showing what's happening in the min.io cache. B is present in the cache. C is not. We'll incur a miss. We'll go to disk and fetch it. Similarly, A is not, but D would be, and so on and so forth. But in every epoch, the only misses we get are capacity misses. Right? Nothing more. That's the guarantee that the min.io cache is providing. Furthermore, we just looked at sort of a single server right now, right? A single server with multiple GPUs. But training could take place on multiple servers. When training with multiple servers today, there's a lot of redundancy in data fetches. So once again, let's look at that example of ABCD. But this time, we've sort of spread across two servers, server 1 and server 2. And in this epoch, server 1 is requesting B and C, and server 2 is requesting A and D. But their local caches, let's say, only had one of those items. Right? So today, when you train, use PyTorch or TensorFlow or whatever, and do distributed training, for these, you would have one miss on each of those servers, right? And you'd have to access disk. One of the remarkable findings when we were working on the CoorDL was, instead of going to your local disk, if you actually went to remote memory, even over commodity TCP, going over the commodity TCP stack to remote memory was much faster, which is crazy, right? If you think about it. And so CoorDL basically uses a coordinated cache and uses sort of a distributed cache across these different instances on which you're running distributed training. Right? And finally, for specific workloads such as hyperparameter search, today there's a lot of redundant fetches that are happening even on a single server. So here I'm showing you two jobs on the same server that are searching different parts of the hyperparameter search space. And they're fetching the same items in different orders, and they're doing it redundantly. That leads to a significant read amplification today. Instead, in CoorDL, we have a unified cache where we can take these items, pin them in the cache, have some sort of reference counting. And once this item has been used by all the jobs that are present in the hyperparameter search, are performing the same hyperparameter search, we can kick it out of the cache. Right? Zooming out, in CoorDL, we have this min.io cache. Once an item comes in, it stays in the cache and doesn't get evicted. And then there are these pre-processing threads that pick stuff from the min.io cache and put them into this sort of cross-job staging cache. And hyperparameter search jobs can pick stuff off there, and when all of them are done using it, it gets out of the cross-job staging cache, and then the raw item is present in the min.io cache. Right? So how does this all work? We've tried in a whole bunch of models. Here I'm showing you sort of a bunch of image classification models, object detection, audio processing models on a bunch of different data sets, and on two different kinds of servers. One, production servers, which have B100s and SSDs, and another which have 1080 Ti's P100s and hard disks. Right? So starting from single server multi-GPU training, here on the y-axis, I'm showing you training speed up with respect to DALI. This is sort of on this production server with 500 gigs of memory and so on, using OpenImage's dataset. And the higher order bit is across these different DNNs that we tried that I was showing you before, we can get up to sort of 1.8x speed up on this sort of SSD-based machine that I showed you, because we're using the min-IO cache and reducing cache misses and going to sort of disk unnecessarily. Right? When we look at multi-server training, remember I told you about partitioned cache. So this experiment is trying to show you the benefits of having a coordinated partitioned cache. On the left-hand side here is the 1080 Ti P100 with a hard disk-based configuration. And on the right-hand side here is the V100 with SSDs. Basically, using the partitioned cache can give you up to 15x better throughput on the hard disk. Naturally, the hard disk is a slower device, but even on an SSD, you can get up to 3x faster speed up with respect to state-of-the-art data loading libraries today, right? And finally, using the coordinated prep cache for hyperparameter search jobs can improve speed by up to 5x, almost eliminating sort of any storage overheads, data stalls in those settings. That's, I don't know, how are we doing on time? Maybe I'm happy to end early, but that's Carja. And I showed you a very, very small sliver of the Fiddle training stack, right? I just showed you the data loading part and what you could do from a systems perspective to better utilize existing hardware and sort of getting you significant speed ups compared to what we're getting today. But hopefully that whets your appetite for all the different things we can do across the system stack. And if you're interested, I encourage you to go and look at sort of the Project Fiddle papers where we've been tackling issues across the system stack. I think one of the reasons I find this area super exciting is because really this is an instance of a big data problem where problems are not sort of localized. There's no silver bullet solution in one part of the stack. Really, you have to look across the stack. That's that.
Thank you, Dr. Amar, for that was a great presentation, especially cutting across the stack. That's something most companies find it difficult to do because it's either hardware-centered or software-centered approaches. I think a lot of people have questions here, at least Kushal does. Do you want to go ahead with your question?
I'm not looking at the chat, but yeah, go for it.
Thank you, Brenna. Amar, thank you. That this is a really good talk and aligned with my day-to-day job. So, so a couple of questions really. Have you, so the pre-processing that you do on the CPU, is that possible to take you to the GPU?
Oh, absolutely. Absolutely. So the results I was showing you at the end was not pre-processing happening only on the CPU. In fact, it was the best of CPU GPU.
Okay, that's very good.
So the baseline we were comparing against was the best of CPU or GPU. It's tricky though. I mean, what we noticed was for some workloads, pushing pre-processing to the GPU might actually be worse because compute requirements of the DNN would be interfering with compute requirements of pre-processing on the GPU. So it might hurt the compute, the regular compute that the DNN ought to be doing, right? And that's why CPU-based pre-processing is also equally important, right?
Yeah.
And so in our comparisons, we would do both CPU, GPU, and pick the best of those as the baseline, and then we would see how much we could improve over that.
Okay, and I was wondering whether you explored GPU direct storage, because that's an ability to copy data directly from storage into your GPU local memory, right?
Yeah, no, this is a very good question. We did not, but it's definitely something that is doable. But we actually stumbled across problems that were even more fundamental right before we got there, which is the OS page cache doing things that were almost unacceptable in this case, right?
Right.
It's sort of going back to, in some sense, we write this in our paper too. We were truly sort of inspired by Stonebreaker, right? Who back in the day for databases said, OS, get out of my way, right?
Yeah.
You don't know what you're doing. Very similar. It's not a scan-based workload. It's a different kind of workload. It's random access, right? We're randomizing every epoch. But it's similar in the sense that the OS is doing the wrong thing for the workload, right? And we can do much better if we just get the OS out of the way. Right?
Understood. Okay, I mean, would love to talk more about GPU direct storage, but I'll take it offline and reach out to you separately.
Yeah, feel free to reach out, and I'd love to talk about it.
Thank you.
I think we have a question from Fanny as well. Fanny, go ahead.
Thank you. Thank you, Amar, for the talk. It was very insightful. Plus, it does a nice cycle to the speaker talk of today. We start talking about...
Fanny, your voice, at least for me, is a little
Can you hear me better?
Muffled.
Still not working?
Keep going. I'll tell you if it is. I can't understand something.
It's better?
Yep.
Perfect. I was just saying that this is a nice close of the speaker talks today, because we start with Chimera, which was talking about an efficient pipeline parallelism, and they refer to pipe dream, which you are the author of pipe dreams. So it's a nice cycle of closing the speaker talks. But my question was around the work that you were presenting right now. So in your experiments and your results, have you seen, because with the trend that we are seeing with machine learning and DNN specifically, we're increasing in size, and at the same time that we are increasing in size, we are increasing our data set that we have to use either for training or for testing. In this effort that you are doing to improve the caching and how we actually do the data loading and prefetch, is that scaling out the way that the model is also scaling out?
Great. It's a good question. Depends on what kinds of models, right, Fanny? I think one of the things that we found, and we talk about this in that whole sweep, is language models. It turns out they're doing a lot more compute per data fetch, right? In fact, the data fetches and preparation in language models is far less onerous than it is in image classification, object detection, audio processing models, right? Because naturally, these classes have to do a lot more augmentation on the data than text data, right? With respect to those models, image classification, object detection, or audio models, etc., growing large, as you scale those models, you naturally also have to parallelize them, potentially using, a variety of techniques like, be investigated in pipe dream, right? And that's in the realm of distributed training, right? This is what I was talking about, of having partitioned caches that you coordinate access to that cache, right? So I'm saying it in a long way, but yes, we did investigate distributed training across multiple servers, and found that the need to coordinate caches there is also as important as it is on a single server, because in the distributed training scenario, today we're doing things where there's no coordination, and hence we're doing a lot of redundant work, right? Instead, if we did some coordination, we could do significantly better, right?
Thank you.
Thank you. Any last minute quick questions before we move on? Okay,
yeah,
thank you.
If not, let me just put it out there. Please feel free to reach out, and you can always ask me questions, right? So.